Hello, everyone. And how are you doing today?
Good to
Hello,
see
I'm good. And you?
I'm doing good. I see we have a guest, Dr. Ferrucci. You could make it. That's great.
you. Good to see you, Dr. Fanasik,
It's
and the
it's
team.
it's great to see you as well. So, Shepard and Caldrian, this is Dr. Ferrucci. She's from Africa University, and she's going to be giving a few guest lectures throughout the course. And she's kind of helped me design what would be in the course, go over the syllabi and kind of the order of topics and things like that. And just really some neat insights to offer. Why don't you go ahead and tell them a little bit about yourself, Dr.
Thank you so much, Dr. Fanasik. Currently, I know Shepard. He has been in the department that I've been teaching, so I'm excited to see a familiar face, of course, and also you. And it's good to meet Caldrin. I actually call myself a friend of Carleton University now because I worked on a project with them last spring, and this time I'm just thankful to Dr. Panasik just inviting me to be part of the work that he's doing. He's doing a great job, especially in the area of climate change. And I know that this is a very topical issue, and I just come in from a position where I have also, have had strong interest in climate change. My PhD is in climate change, especially looking at climate variability in Africa and how it's affecting households from a gender perspective, also looking at how it affects men in a different form than it affects women. So I've actually been also engaged with projects on the ground at Africa University with communities, and so I know that this is also new territory for me in the US in terms of community work, but I look forward to engaging communities around the US or maybe Claflin to see what's happening to them. Just almost a replica of what I did in Africa. I want to see how it's affecting people who live in the cities. So my major interest really is in the impact of climate change on communities. How is it changing livelihoods? How is it changing even maybe the structure of their economies? How are people navigating this climate change terrain? So I'm very excited to be here and also to explore these issues with you guys. Thank you so much, Dr. Fanasik.
No problem, no problem. One of the things that we've done a lot in here is I like to put things in the context of climate change issues that we're facing in our local geographic areas. So I'm wondering if everybody could share with Dr. Farousa, and if you could share as well, just some significant impacts personally that you're encountering in your area. Caldra, do you want to start?
Yeah, I was going to start. Um, or I think I'll use not just my state, but I think I'll just use the U.S. as a whole. Of One impact of climate change is a particular strand of bacteria, cyanobacteria to be exact, growing and propagating in areas of the northern United States, such as upstate New York and around the Great Lakes, and areas which this particular strand of bacteria hasn't really grown in the past thousands of years, but due to the problems of climate change, they're spreading in far northern places of the United States. So that's just one, of course, of hundreds that I could probably, kind of pick a little bit off of. But I think that's the most important one to me because I've kind of been having direct work with that one for the past 2 years.
Did I get you well? Did you say salmon bacteria?
Cyanobacteria.
Okay, cyanobacteria. Okay.
Who else would like to go next? Is it Hugh? Are you there? Zach? Could you turn
Hello,
on your
sir.
camera if you could?
Hello, hello everyone. I don't know if
Hi.
you can hear me well.
I think it came in just a little bit late. I was introducing Dr. Farusa. She'll be doing some guest lectures throughout the course. And I was wondering if you could just tell her a little bit about yourself and some of the climate change phenomenon that you're encountering where you live.
Um, Now I'm staying in Zimbabwe, Mutare, but I'm from Mozambique, Chimoio, and the main reason because uh, I'm doing this program because uh, even when I finished my degree, I started to work with agriculture and sustainability movement. Right now, I'm working in a project called Rosetta Pearl. Uh, when we are finding, and our mission is to facilitate the sustainable management of post-consumer fashion waste, and to main reason to how can I say to promote also the fashion consumption was using consumption model. In this project, we are using the artificial intelligence when we are sorting the clothes and to find a way to reduce the consequence of the waste in the nature. So I think with the in this program I will have skills to help to improve this project and other things that I'm working. I came late, so I don't know if I replied well your question or what.
Yeah. And Shepard, did you want to add anything?
Hello, Prof. All right, my name is Shepard Gwiza. I'm an agronomist by profession. I've worked in the agricultural sector. I've observed that climate change is affecting mainly smallholder farmers. And also, due to climate change, I've noticed that there are serious diseases emerging in the agricultural sector. For example, we have the fall armyworm, which is affecting farmers. And also, we have the likes of absolute tutor, which is affecting tomatoes. So climate change is a serious issue in the agriculture sector. Thank you.
Excellent. Excellent. Okay, well, as usual, did you want to say anything else, Dr. Fruser? I'm going to go ahead and get started a little bit with how we normally run class so you can kind of get a feel for it.
No, you're okay. You can go ahead. I'm just fascinated by all this stuff that's already going on. That's pleasing that there's hands-on of work in the area of finding out the impacts. Thank you for enlightening me. Go ahead.
Sure. Sure. So far, we've talked about a few things. We started off talking about just the scientific method and how we know what we know, and if we can have confidence in the numbers that we're using, as we're trying to understand climate change. We talked about why we use temperature anomalies when we talk about weather and climate, and how anomalies allow us to, one, use fewer thermometers because anomalies can measure temperature differentials in larger areas. We looked at the global surface thermometer record, as well as a number of other records to look at the data of the temperatures we're seeing now and how to compare them to the past. And as we know, to calculate a temperature anomaly, you always have a reference period where you take the average temperatures for that thermometer during that reference period, and you subtract those from the values of the record you're looking at to get your anomaly. And so we looked at the anomaly in a number of different records. The surface thermometer record. Can anybody tell me what the value was for the surface thermometer change since the late 1800s?
1.1 degrees Celsius.
Okay. And what about for bulk ocean temperatures? What was the change that we saw there?
0.6 to 0.8 degrees
Yep.
Celsius.
Very good.
0.6.
Very, very good.
0.6 to 0.8, I think so.
And what other records did we look at to try and gain some kind of glimpse into if this is actually happening?
You use the satellite record, surface thermometer record, sea level,
rise.
sea
And
level,
sea level. And
bulk ocean temperature, and the amount of ice melting. I can't remember the exact name of it, but the indication of or the amount of ice that's melting within the two poles of the Earth.
And so, for example, with Greenland, about how much ice are we losing a year currently? Does anybody remember that value?
600. Is 667 gigatons or is it 67?
271. 271.
Okay, I'm way out.
Yeah.
267. 267.
Okay, good, good. And I think it's important to have those kinds of values at the ready and be aware of them because we're going to be using them, throughout the course. And when we're justifying, the types of interventions that we want to justify, we're going to really need to be facile with those climate details. So we looked at how the Earth is changing, and would you all agree that the conclusions are fairly solid that we're seeing warming on the Earth? Okay,
Yeah.
good. Okay. So then the next question becomes, well, why is the Earth warming? I mean, we've heard various, ideas from various folks about why it might be warming, but what does the science tell us? And so in order to get to that, we really have to talk about kind of the physics of warming. And so in our last lecture, we talked about power and energy and how they're interrelated, as well as the Kelvin scale. Usually, I like to start class with a quiz. So today is no different. I'm going to go ahead and share my screen and pull up a quiz real quick. So where is, there we go. So, okay. So let's start with this quiz here. The sun shines 1,360 watts of energy onto a square meter of an Earth satellite for a half of an hour. How many joules are transferred? So I need you guys to take out a sheet of paper and give me a number on that. Okay, and when you think you have a number, go ahead and say something in chat. Don't put what the number is. Just put down, got it. Okay. Shepard's got a number. Okay, Caldrian. Zach, how about you? Okay. Everybody go ahead, paste your numbers in. Curious to see what they are. And then I'll kind of walk through the problem. Go ahead, paste your numbers in into the chat. Shepard and Zach, you want to go ahead and just put your numbers in? Okay. So a nice variety. Okay. Does anybody at this point feel really lost? You guys, I'll go ahead and walk through it. Okay, so the first thing we need to do is figure out which formula we want to use. Remember, these are our three main formulas that tell us our basic relationships between energy and power. And so for problems like these, you always want to look at, what information are you given, and what are you trying to figure out? So what are we given in this particular question?
You are given time and watts. Watts
And
would
watts is a measure of
energy.
watts is a measure of, is it
Power.
energy? It's a measure of
It's
power,
power.
right?
Yes.
So power is the amount of energy divided by the time, right? So if we look at this, so what is the unit of a watt, since we're talking about power? What is a watt equal to?
Well,
Remember, our watts were equal to, I'm going to go ahead and pull this here.
would it be equal to a joule? 1 watt, 1 joule.
Remember that power is a rate of flow. So energy, which is measured in joules, and that's kind of the capacity to do work. When it comes to power, that's expressed in watts, and that's about moving energy from one place to another. Or how much energy, how fast are you moving it? And so that's joules per second. So 1 watt would be 1 joule per second. And to give you an idea about, what a joule might be, a joule is about the energy required to lift an apple about 3 feet. And so if you're going to do that in a second, you've expended a watt of power. And so a watt is a rate. It's how fast the energy is being transferred. And that's what power is. That's why you look at the energy and you divide it by the time, and that gives you the power. So if we had joules per second, that would be power, and a joule per second is a watt. Okay. But in this particular one, we're given watts, which is power, and time. So if we're given power in time, you got to look through these equations to see, on the right side, which ones have power in time. There's this one, and it's energy equals power times time. And if you look at this, we're asking for how much energy, right? How much energy is being transferred. Okay. So which of these equations do we want to use?
Is that
Middle.
the second one?
Right. Yeah, the middle one. Okay. So we're going to use that one. Does that change how you do the calculations at all? So go ahead, and if you didn't do that part right on your piece of paper, go ahead and stick in the information how you should have it. So we know our power is 1360. That's joules per second. And a half hour. Remember, since our watts are in joules per second, we need to have everything in the same units. So we can't use a half hour. We have to convert a half hour to seconds, right? And so 60 times 30. So there's 60 seconds in a minute times 30 minutes in a half hour. That comes up to 1800 seconds. And so all we need to do is multiply these two in our formula, and that's going to give us 2,448,000 joules, 1,000 joules, and we can abbreviate that to 2.448 megajoules. Does that make sense to you guys?
Yes, Prof.
Okay. Okay.
Yes, sir.
Do you want to do one more practice one?
Yes.
I'm seeing a yes on this. Okay. Okay.
Yes,
Well,
sir.
fortunately enough, I have another practice one set up just in case. Notice on this one that I'm using the sun shining onto an area. I picked an Earth satellite because I don't want to talk about atmosphere yet. We're just talking about the sun shining on something. And we know when the sun shines on stuff, the stuff can get hot. It'll heat it up. There's energy transfer. So the 1360 watts per square meter, we're going to see that number come up over and over again as we start creating climate models and stuff like that. But I digress. So here's the second one. So we have a power source that contains 50 kilojoules of energy. Okay. And we're going to use it to power a 100-watt light bulb. That's a lot of light bulbs these days. You can find 100-watt light bulbs, pretty bright. How long can you keep the light bulb lit using that power source? And notice I don't put any of the equations on the quizzes or the slides because those three equations you pretty much need to know. And they're all derived from each other. So all you need to know is one of them, and then you can always rearrange it by putting, solving for any one of the letters to give you all three equations. So you really just need to know one, which is power equals energy divided by time, which is our definition of power. That's why a watt is joules per second. Energy is in joules, time is in seconds. Okay, I got a count. Shepard's got one down. Is anybody surprised by the number that you're getting? Okay, remember, just keep in mind, if I like for folks to have kind of a sense of the energies are. Remember, a joule of energy is about the energy it takes to lift an apple up about 3 feet. So 50 kilojoules, you'd be lifting 50,000 apples up 3 feet. That's the energy that we're talking about. And so we're going to use that energy to power this 100 watt light bulb. Out of our list of equations, which one should we be using?
The last one.
Right,
The last one.
because we're given energy and we're given power, right? And so now we need to know the time. Okay, fairly simple. We need to make sure we're all in joules and seconds. So 50 kilojoules is 50,000 joules, and 100 watts is 100 joules per second. When you divide these, the joules cancel out, and you get 500 seconds, or about 8.3 minutes. Does that surprise you how much energy? Think of lifting 50,000 apples up by 3 feet. And that amount of energy runs a 100 watt light bulb for only 8 minutes. And that's hopefully, as we'll learn later on, traditional incandescent light bulbs are horribly inefficient with their energy usage. We see a tiny smidgen of the energy that is coming out of a light bulb, because only a tiny smidgen of that energy is in the visible light spectrum. The rest of that energy, most of it, 95% of it, is actually coming off in the infrared. And so we don't see it, we don't sense it. Okay. But we'll talk about that later. What we're going to talk about now, though, is energy transfer. This is very apropos. And so if we want to think about climate, we have to think about, where does the Earth get all of its energy from? We know the sun is shining on the Earth. Well, how is all that energy getting from the sun to the Earth? How is it transferred physically? We're talking about going 150 million kilometers. That's the distance from the sun to the Earth. Okay. And so how you have to transport that energy through the vacuum of space. And so all of that energy is being transferred through electromagnetic radiation. And you can think of it as flying off the face of the sun are these little packets of energy. We call them photons. Okay. And it's the photons that are carrying that energy that the sun is shining and radiating on the Earth. The amount of energy in any one of those photons is determined by what we call the wavelength of the photon. And just as a little background, which you should all know, let me see, where's my second. Do you all know the parts of a wave, or do I need to go over that? Maybe I will. So if you have a wave, I'm just going to have set up a standing wave here, like a sine wave. This is our traditional kind of a wave. And there's a couple features about the wave. There's the tops of the waves, those we call peaks. The bottoms of the waves we call troughs. Some people will call the peaks crests. So you have the peak or the crest and then the trough. The distance from 0 to the height of the crest is what we call the amplitude. That's the same thing as the distance from the height to the bottom of the trough. That's our amplitude. Our distance from one wave peak to another wave peak, that's the wavelength, okay? And in our little packets of energy and these photons are coming off at different wavelengths. So some of them have really short, fast wavelengths. Other ones have long wavelengths. And the sun emits a broad spectrum of these different packets. Do you know which ones have more energy, the short wavelengths or the long wavelengths? Does anybody know? I see you saying short, Desire. Yeah. So it's the shorter wavelengths that have more energy, okay? And the longer wavelengths have less energy. And that's important to know in our basic understanding. But there's all sorts of radiation coming off of the sun in this form of electromagnetic radiation. And electromagnetic radiation is a lot of what we tend to think of as different things, but they're all actually the same thing. So, you know, you're familiar with visible lights. You've heard of X-rays. X-rays and visible light are actually the same thing, except for X-rays have a much shorter wavelength than visible light rays. Same thing as you may have heard of gamma rays before. Gamma rays are, gamma rays, again, are short wavelengths, high energy photons. The ultraviolet and infrared rays are also the same kind of electromagnetic radiation as are microwaves that you see like in a microwave oven or radio waves. It's just a difference in wavelength. So what I'm showing you here is a fairly broad spectrum of electromagnetic radiation. And I do want you to get somewhat familiar with the range of visible light, because we're going to have to come back to those numbers quite a bit. So very short wavelengths or high energy would be these cosmic rays. Gamma rays are also very high energy. Now we're going lower in energy as we get to X-rays. X-rays are on the order of 1 nanometer wavelength. So a nanometer is 10 to the minus 9 meters, or a billionth of a meter. So really, really tiny little spaces in between those waves. And then as the waves get longer, these photon packets are a little bit less energy. That's where you start to get into the ultraviolet spectrum. The ultraviolet is usually less than 400 nanometers. And then we start, and we can't see that. The cones and rods in our retinas can't sense those. They don't have sensors for that frequency of light or that wavelength of light. Once you get into around 400 nanometers to about 700 nanometers, then you're in the visible light range spectrum. And the only, we perceive those differences in wavelength as different colors. So the shorter wavelengths are closer to blue, the longer wavelengths are closer to red. And then after a certain point, after a little over 700 nanometers, our eyes again, the cones and rods that detect light in our eyes can't sense the infrared, so we don't see that. Now, as you stretch out further, so infrared is basically anything beyond, I would say, about 800 nanometers up to 1,000 will be your infrared range. And then you'll start getting into microwaves, which are longer. And depending on the wavelength, you can penetrate through different substances. Like as you get to radar can or radio waves can bounce through walls, for example. And so radar, radio waves, broadcast cast bands for television, these are all your longer wavelengths. But think of our visible light range is in a fairly narrow range between about 380 to 750 nanometers, in that range. Questions. Why do you think that we have evolved to see in our visible light range? Why don't we see in a different spectrum? I mean, why don't we see in gamma rays or X-rays or radar waves? Why this specific? It's a very narrow range that the receptors in our eyes have been evolved to be able to sense. So I'm curious what your thoughts are.
Aren't some of the listed wavelengths, aren't they dangerous? For example, I believe the gamma rays, aren't they dangerous? So it wouldn't be conducive to any type of survival for us to be able to see within that spectrum.
So you're
And this
saying
just a guess.
what you can't see can't hurt you? Just because you don't see them, they're not there, they're not damaging you. We have gamma rays coming down all the time from the sun. You are right that they are harmful. X-rays and gamma rays can be very harmful. The particular bonds in our DNA vibrated about the same wavelengths. They can absorb gamma rays, and so that can break bonds in our DNA, which cause mutations, and some mutations can lead to bad situations like cancer. That's usually one you have to worry about. Fortunately, we have many repair enzymes that are constantly repairing this damage. But that doesn't get at the question to why do we see in our visible light range and not in gamma rays or any of the others?
Can I try? I'm
Yeah.
not really sure that I believe because the visible light range is the range where it's able to stimulate the what do you call this? The retina. Yeah.
Yeah, the
these
rods and the
rays are
cones,
ones
those are
that,
protein receptors in your eyes. Go on.
so they're the only ones that can stimulate the cells of the photoreceptors around the retina or in the retina, whereas the rest of the wave they just pass through and we can't intercept and decode them.
So what you're saying, Desire, is correct in that those photoreceptors do only, they only interact at those wavelengths, and the other stuff goes past. But it would be just as easy for life forms to have evolved a slightly different protein that absorbs in a different range. So you're right for the reason we can only see visible light, but it could have been that we could have evolved to see in a different range. Why do we see in this range? The reason why I like asking this question is because it really gets at fundamental relationships between us and how we interact with our environment, and how our environment interacts with us and affects our evolution. We're going to see that throughout the course. So why do we only see in this light range? Shepard, you have a guess? Everybody else is gone. It's time for me to shoot you down.
No, bro.
Okay, let's look at it in a different light. Say I'm an organism that's growing on a planet that it has mostly chlorine gas as an atmosphere. Okay, And so everything's really cloudy and misty and foggy. That is gonna be hard. It's gonna mean that my sight isn't really gonna provide me much of an advantage, right? If a lion comes stalking me, all I can see is clouds. But what if I said, well, there's a frequency of EM radiation that goes right through chlorine gas, isn't blocked by chlorine gas whatsoever. So the chlorine gas wouldn't stop it at all. Say we're talking about microwaves. If my eyes could see in microwaves, now the chlorine gas wouldn't be an impediment. See where I'm going with this? The reason we can see in the visible light is because our atmosphere, which is composed of just a few different gases, is pretty much transparent to these wavelengths. We would want to pick a range of EM radiation that the air around us is transparent to. If we picked a different wavelength that doesn't pass through the air, then it wouldn't be much good for us. We'd always be seeing this cloudy gas. So we had to evolve if we wanted to have sights that can see far, we needed to pick wavelengths that were basically invisible, could pass right through gases, the gases in our atmosphere, and also water, right? So this light range also goes right through water without any impediment. Okay. So that's a large reason why we've adapted to this light range. There's a couple other reasons one can think of. So we could have perhaps adapted to see more in the infrared. There are many creatures that can see in the infrared, various varieties of snakes, for example. But generally, those are nocturnal creatures because they're looking for the infrared, the things that glow in the infrared at night. And so if we were more nocturnal, we might have been able to see further into the infrared. But since we're daytime creatures, we have a lot of electromagnetic radiation coming from the sun. We want to be able to see in a range where the atmosphere doesn't block those particular types of rays. If we saw in the far UV, for example, well, the ozone layer above our planet blocks much of the ultraviolet radiation, the high UV. And so if we only saw in that range, the sun would be very dim if it would be seeable at all, because all that electromagnetic radiation is kind of getting blocked. We all on the same page with that? So it's important to kind of remember this range. Now, the range I have in this slide is between 400 and 700 nanometers, about 750, between 380 and 750. And that's in nanometers. In the textbook that we're reading, you'll often see wavelengths in microns. So a micrometer is a difference by 1,000. So 380 nanometers would be 0.38 microns or micrometers. Okay, and so be aware of that when you're reading the book. Some of our formulas that we're going to use in our climate model will mostly be around probably micrometers. So if you remember the range in nanometers or micrometers, I would take either one. But it's just a difference of a decimal point. If you're talking about nanometers, we're 380 to 750. If we're talking micrometers, it would be 0.38 to 0.75, that range. Didn't get as far as I'd like today, but we'll try and pick up the pace on next Monday. And where we're going with this is we're trying to see what happens with all that energy from the sun. We know that's our main energy source from the planet. It shines down. What happens from there? And so it's important to really understand what the different wavelengths are, how much power is being transferred, and then I'll kind of show you and walk you through the simplest of climate models, which show what happens when you shine light on any kind of an object. You get this black body radiation stuff. We'll talk about that. And then what happens when you stick an atmosphere on it. And then what happens when you stick an atmosphere on it that has different chemicals, like carbon dioxide, for example. We'll talk about that next week. Any questions? Did going through those examples, do you feel confident now you can do those kinds of equations with the basic power and energy? Okay, we're not going to do, this course is not going to be focused on math and physics, but I do want to do enough so you really get exactly why the Earth is warming up, where the numbers come from, and so you understand when people talk about, oh, we use climate models to predict these things, what exactly are those climate models actually modeling, and how are they calculating those things? You'll see a great treatment in the book on all this material in chapter 3, and we'll be doing chapter 3 and chapter 4 in the next week or so. Okay, everybody, thanks a lot. I'm going to go ahead and post this video. The one from last week is up. I'll post this new one. I'll also send out an email with a YouTube link as well. Thanks, everyone.
Thanks.
Dr. Panasi,
Goodbye.
Thank you, Prof.
Yeah.